Hi, everyone. Welcome to the Deep Engineering Live interview series, where we bring you insights from engineering leaders, architects, and authors who are shaping how modern systems are built and scaled. I'm Saqib Jan, editor in chief of Deep Engineering, a weekly newsletter and a publication where we explore the ideas, practices, and people driving engineering forward. Today, I'm really excited to be speaking with Brian Allbee, author of Hands-on Software Engineering with Python, published with us at PAC. Now it's in its second edition. Let me bring Brian on the stage and we can. Brian,
Greetings.
it's great to
There
have
we
you.
go. Greetings. Thank you. Pleasure to
Welcome.
be here.
Well, Brian, to start off, could you tell us a bit about your background and the kind of systems you've worked on over the years?
Sure. I've been programming almost exclusively in Python since early in 2012. Prior to that, I also worked in C#.NET and Cold Fusion Markup Language and PHP for web application development. But I landed on Python at a job that I started early in 2012 for an ad agency where they needed somebody to come in and basically build an internal application that was more performant than their off-the-shelf application for asset management purposes. Fell in love with the language a little bit before that position started, actually, but was very, very happy that the language audit that I did kind of reinforced yep, Python is the way to go on this because it had everything that they needed to have it do. And I haven't looked back since. Since then, I've done, some client-facing cloud management application work, handful of customer-facing applications that I can't get into too much detail on because they're still covered under NDAs, despite the fact that the company I worked for at the time is technically no longer in existence. The last 6 years, most of the last 6 years, I worked doing machine learning implementation or integration for Dice.com on their a team that eventually became the Applied Data Science and AI team, I think is what it ended up being called. Currently, I'm working contract for a place called Apex Systems, doing backend system development in AWS cloud context with step functions and Python lambdas to deal with health insurance processing issues that they needed help with. That's where I am today.
Great. We're really excited that you are here with us today. Just before we launch into questions and our discussion, I just quickly wanted to thank our attendees today. We welcome to you our live interview series. Deep Engineering is a weekly newsletter. I'll be sharing the link in the chat, and do use that to interact with me or Brian. But if you have questions, please use the Q&A section over there for asking your questions. I'll display them on the stage. Maybe I might even bring you on the stage if you're comfortable. And today, we will dive deeper into the software engineering mindset and what it means to grow from a programmer to senior engineer. And Brian is a perfect candidate to answer those questions for us. We will also discuss refactoring, scaling, and designing Python systems, and also touch base around testing and CI/CD pipelines. All right, so we will dive into our questions now, Brian. Perfect. So, Brian, from your perspective and your experience in the industry, what distinguishes a true software engineering approach from just basic programming, particularly for Python developers, who are working on real-world systems?
I think learning to think in terms of systems, not just implementations, is probably the main thing. I feel that holds true whether the backing language is Python or not. And it doesn't stop with just the systems that an engineer is writing. On the technical side, it extends out to the entire tool chain, anything that shapes the code itself or determines how the code is managed or handled. But it also extends to, call them non-technical systems, in the sense of a set of principles or procedures that define how something is done. I basically feel that programming is really focused on making sure that the code is correct, the correctness of the code itself, where software engineering starts expanding out into more of a focus on sustainability as change occurs.
And for developers, Python developers who might be aiming to move into senior or staff engineering roles, given that AI is everywhere now and you need it to grow even in your job, in your career. So what skills or mindset shifts do they need beyond just raw coding proficiency?
I think that same systems-oriented thinking is still the big dividing line, and I believe that that will hold true even if LLM-based code generation turns out to be the next big thing that all of its proponents argue it will be. Even in those scenarios, manual interaction with the code itself, being concerned at the level of the syntax of the code itself, while it might dwindle over time, there's still going to be sensitive domains where there's going to be some of that. But more importantly, the need to understand how that code fits together, even if you didn't write it, and why it fits together the way it does, will still be very important. Hand in hand with that is a broader understanding of the problems that are being solved. Software engineering, I think, like every other engineering discipline I'm aware of, is concerned with solving problems, usually while operating within some set of constraints. Software engineering focuses on solving those problems by creating systems, and that goes back to the whole systems-oriented thinking. But solving the problem requires understanding that problem first. Even if code generation becomes largely or completely automated, someone still has to own that system and understand its constraints and its potentials for failure and how it's expected to evolve over time.
Interesting answer. Thank you. That's helpful. Let's also touch base on refactoring and scaling Python systems. Many Python projects start as simple scripts and then grow into complex, long-lived systems. So, what are some of the best practices for updating, refactoring, and scaling an existing Python code base as it would evolve?
I think most of the paths to success in that context, at least the ones that I can think of that I've seen, don't really start with the architecture, but with discipline behind the process. The approaches that have worked for me or that I've seen work well for others include keeping things as simple as possible, wrapping processes that get used over and over again into functions or methods or whatever context might work best whenever possible, not being afraid to use structured data. If you're working in a team, make sure that the team has some agreement about how much in-code documentation and by extension comments are expected and what it should provide. Same kind of team level agreement about what kind of code standards you want to apply and stick to those until something comes up that isn't covered. Revise them as needed. It's a growing process. Writing code with an eye towards making it testable is key, even if there's not an immediate need for testing. I think future you, if you're writing good tests, will come back and would thank you if they could.
Justin. And over here we have a question that I would like to bring on stage, and then we can just move along. I can just ask you more questions. So we have a question from David Ferguson. Fagerstone, how critical is containerization to scaling systems?
So containerization is one of the more popular mechanisms, but it is not the only mechanism that is out there. I think most of the experience that I've had with containerization has been in a cloud-oriented context, and the alternatives in an AWS context at least include things like Lambda functions, which technically are their own containers, but you don't have to worry about containerization as one of the factors to your code that you are concerned with. You're literally just writing code to fit inside the context of that Lambda container and letting it go. It's a good skill to have. Most definitely something that is going to be of use and interest in a lot of jobs these days, but I don't know that it's a critical skill for all cases in and of itself.
Interesting. I hope that answers the question for David. That was good, profitable answer. Thank you so much, Brian. I'll mark it as answered. If anyone had any questions, please post them in the Q&A section. We'll move to the next question. I also wanted to basically ask, as you were discussing about scaling, and maybe if you could please share an example from your experience of tackling technical debt or maybe redesigning a Python system to improve its maintainability and performance?
Honestly, I really can't. I don't have any dramatic war stories here because I've worked with generally exceptionally healthy teams that treated technical debt as a first-class concern, not as an emergency. Now, that said, technical debt is one of those product level priorities, right? Whoever's making the prioritization decisions is going to be in control of when those get tackled, if they get tackled. If there is significant technical debt, making sure that you can communicate effectively, here's what the impact of this technical debt is to your product level people or whoever's making those decisions is going to be a key thing. And that means, basically being able to sit down and say, look, I understand that you don't want us to deal with bug A or whatever it happens to be, but if we don't deal with this, it's going to lead to this, it's going to lead to that, and that's going to go to here. And the longer we put that off, the more likely it is that it's going to lead to a really significant problem, and the longer it's going to take, potentially at least, for us to get past that.
Interesting. Thank you for that answer. Let's just also talk about upfront design and upfront design versus agile. So modern teams often grapple with how much upfront system design to do versus diving straight into coding. So how do you find the right balance between careful architecture, which is like planning, and rapid agile iteration?
Right. I think understanding the full final scope of a project, even if it's just at a very high level, is critical to one side of that balance. The other side of that balance is knowing, again, even if it's just at a high level, what constraints and non-project expectations are in play. You mentioned Agile. Even if some form of Agile is not a part of the team's day-to-day processes, there are some takeaways from Agile that I think can still be beneficial. The entire idea of delivering working software frequently on some sort of a cadence, though I would add for whatever value of working applies, is one of those. Iterating against the smallest deliverable units that can be identified, not technically an explicit part of the Agile manifesto, but it's pretty strongly implied, would be another major factor, I think. Knowing the eventual goal for a system should ideally also allow a team to plan for tighter and more focused increments of work. I don't think the real risk is too much design or too little. It's designing without understanding the constraints that are involved.
Okay. And in your opinion, maybe, or probably from your experience, is just enough upfront design important to prevent costly rework later? And maybe how can teams achieve that sweet spot in practice?
Yeah, I think it is. I don't think it's the only way to get there, though. It's almost certainly going to be the easiest. There's a lot of literature and a lot of guidance available to lead you down that just enough design path. I mentioned before the idea of iterating against the smallest deliverable units possible, and I bet that would be a good, solid first and best step towards hitting that sweet spot. But I think that's probably going to be the main. Yeah, I think that would be the main one. Iterating on the smallest meaningful units of work, I think, is going to be the most practical way to find that right balance between the design and execution.
Interesting. And about Python is also, I just want to touch base also on embracing those modern Python features. So Python has introduced features like data classes and optional static typing, which is like type hints, in recent versions. And we've seen new high performance like type checking tools emerge to encourage developers to adopt type hints. So how have these modern language features changed your approach to probably designing Python software? And maybe how would you recommend that engineers fully embrace type hints in large Python projects?
So not as much as it might sound like, actually. I mentioned that before I turned to Python, I was working with C#.NET, and that's a static language, static typing, compiled language. And I came to really like the idea of static typing from a programming perspective, even in dynamically typed languages like Python and JavaScript for that matter. If you dig back far enough into some of my very old and unsupported blogs these days, You'll find that I even wrote some blog posts about implementing that sort of a structure in Python back as far as version 2.7. I definitely recommend using the typing system that's in the language right now. At worst, it's additional documentation that modern IDEs can pick up on to help an engineer who's working with the code. With the inclusion of just one third-party package, I like TypeGuard myself, but there are others, I'm sure. It's possible to achieve runtime type safety and static type-like behavior in Python code. And other, pre-deployment tools, MyPy, I think, is the one that I've seen the most of, is going to pick up on your static or your type hints to give you some extra quality control going into that process. I think that whether you enforce types at runtime or not, the design clarity is worth it.
Interesting. We have a question from somebody, and I want to bring it on the stage. And all right, it is, as you might be able to see it, do a lot of setup before tests, collecting firmwares, configs, using other tools to prepare the files and preparing the environment. How would you automate this in GitHub Actions? It's from Kennedy Nizov.
Well, so the short answer is some variation of I'd write Python code to do it because of Python. But yeah, without knowing some of the specifics involved, I don't know that I could give a detailed answer. If those configurations and firmwares, well, okay, I'm not sure about firmware in this context. If the configurations are things that can be stored in the repository, keeping those, as long as there's no secrets in them, in the repository, strikes me as a good first step for that. Other tools to prepare with files and preparing the environment. Yeah, honestly, dig around, look for Python libraries that support whatever you need. I'd be very surprised if you couldn't find something out there in PyPy. There's 700,000 packages there, last I checked, that will get you a good part of the way towards achieving whatever goal you're looking for. And if you can't, well, I don't know. Start digging into how can we automate it just kind of piecemeal. What do we need to do? First step in collecting firmwares, and can we automate that? And iterate against that, going further and further into what else can we automate. I don't know that that's a very good answer, unfortunately, but that's where my head goes at this point.
Thank you, Brian, for answering that question. I'll mark it as answered. And if any follow-up questions, please post them in the section. All right, let's just move and talk about data modeling, particularly data classes versus Pydantic. So ensuring data integrity is and has always been crucial in software systems. And we have libraries like Pydantic that have become very popular for defining and validating data models in Python across various domains. So in building robust Python applications, how do you approach data modeling and validation?
All right. Honestly, I think it depends on the scope and intentions of the project. Pydantic is great for projects where there are complex requirements that can be derived from something like a JSON or OAS schema. It's also good for projects that are responsible for generating those JSON or OAS schemas. The downside to that is it's a larger package. I think the last time I looked at it, it was coming in at 2.5 megabytes or so for the module itself and its primary dependency. So if package size is a concern, that might not be the best choice. There are other options though. If package size is a concern, fast JSON schema combined with something like regular Python dictionaries and lists is a solid alternative, and it's much smaller. If there's no need for any kind of schema documentation, but there's still a desire for type checking, type annotated Python classes will probably get you 80+% of the way there, in my experience. If you need mutable data structures, and that's all that you need, data classes are a good option. If immutable data structure is the need and type checking is still not a concern at the level of the code structure, I usually start with something like a named tuple. I think the right data modeling tool depends less on the popularity and more on the system's constraints and the scale and the scope of the project and its longevity.
Thank you. Just moving on, I want to also ask about testing strategies in Python. So What are your go-to best practices for testing Python systems at scale? For example, how do you balance unit tests versus integration and end-to-end tests, and also ensure that the test suite remains reliable and useful over time?
Yeah. So for my own projects, I tend to like a testing approach that exercises valid and invalid inputs for all of the parameters of every callable in the project. If you combine that with judicious monitoring of missing lines in a code coverage report, that has served really well for me in making sure that the targets of those tests are being both thoroughly and realistically exercised. In a working environment, I like for the team that I'm working with to come to some sort of a consensus about how the tests are organized, what tools are involved, and so on. I've seen what happens when different engineers who aren't communicating with each other each go their own way. The tests that result, even if they're rigorous and well thought out, are oftentimes difficult to follow across different test modules because different people will write tests in different ways. When integration or end-to-end testing isn't feasible, I try to push unit tests closer to behavioral testing, even if that increases mocking complexity. In those kinds of scenarios, unit testing can still go a long way. It's just a lot more time consuming with some frequency. Ultimately, though, tests are most valuable when they reflect how the system is actually used, whether that's managed at a unit testing, integration testing, or system testing level, not just how that testing code or the code itself is structured.
And Brian, I just also want to ask a question around AI over here, because we also see a lot of rise in AI testing, even agent to agent testing. So we are seeing that AI is being used in areas like test generation, debugging, and even test maintenance. So from your perspective, how should engineers think about AI in testing, without compromising reliability and confidence in their systems?
Right. I think the important thing, the fundamental important thing there is going to be getting some sort of consensus from anybody who's involved, all of the stakeholders and anybody who's going to be held accountable for failures in the code as to what the guardrails need to be. I like AI from the standpoint of code generation for
Mm.
things that are not sensitive. If it's touching somebody's lives or livelihoods, I don't want just randomly generated code to be out there without really good guardrails. I think probably the best, I won't say the best approach, the approach that I've seen and tried myself that has the most promise, I think, is to take sort of a test-driven development approach and define a test suite and only allow humans to modify that test suite. Make sure that it's really good, really solid, really rigorous, and covers all of the business needs, everything that you can come up with. And then you can let an AI process go to town on whatever. As long as there is a clear boundary there, you can, hey, Claude, you can write all the code you want. It must pass this test suite. You do not get to modify that test suite. Let it go to town. At that point, I think you're probably about as well covered as you can be. Yeah, I think that's probably about as far as I'm willing to go on that at this point.
Yeah, interesting. That's helpful. Thank you so much, Brian. And also talking about CI/CD and automation for Python projects, how should maybe Python teams set up CI/CD pipelines to improve code quality and deployment reliability? For instance, using GitHub Actions or other tools. Maybe tell us some best practices that you've seen help the most, and maybe pitfalls should be avoided when automating Python build and deployment.
Well, okay, so minus some activities that may be specific to Python, packaging jumps to mind. The goals are all the same for CI/CD, regardless of the language involved. You have to fetch the code, you have to test it, you have to build it, package it, whatever that middle step is, and you have to deploy it. I think, well, the basic sequence is common across the board. There may be additional tasks, things like checking that a deployment process is well formed, or there may be aspects that are not tied directly to the code, but the baseline things are all pretty much the same. So it's very circumstantial. The main value that CI/CD adds isn't necessarily the automation, it's the fast, automated, trustworthy feedback that you get from one of those processes. So I would say look for places where you can generate that feedback, find the breakpoints that are going to happen, and make sure that anything that fails gets surfaced in a meaningful, timely, and useful fashion.
Thank you. Let's also talk about designing cloud-ready Python applications. So,
Sorry, I'll say that again.
Let's talk about cloud-ready Python applications.
Okay.
So, cloud-ready architecture requires certain design principles. So, in your view, what makes a Python application cloud-ready?
Again, that's very context dependent. Cloud ready can mean different things to different organizations, different teams, or even individual people. A containerized application is cloud ready, provided that it can be deployed appropriately, but so too are functions as service constructs like AWS Lambda functions and their equivalents in other provider spaces. It all depends ultimately on the final deployment expectations. Some key things to bear in mind that may or may not be specific to a cloud context include leveraging environment variables, I think, to help control behavior in different cloud accounts or environments within those accounts. You'll find that can carry over from local development to deployment processes and build pipelines, all the way out to your final deployed product, wherever it is. They can always be replicated and manipulated locally in that kind of a case, and it makes things easier and faster to change in a deployed application or some sort of a component-based structure than having to redeploy an entire stack. Be aware of and look for, actively seek out systems that cloud providers offer for things that you need to try and deal with. Secret storage is a great example. And write your code so that those systems are in use and minimized, right? So you pull a secret in one time when a container initializes or Lambda starts up, and then don't touch it after that. As a side note, it's not cloud specific, but it should also go without saying that don't put secrets in your code in a repo. Don't. Know the best practices and constraints for your final deployed code. And if you don't explicitly test that they are accounted for, at least be aware of their potential impact. A great example, I think, is AWS Lambda functions. You cannot run a Lambda function for more than 15 minutes. So have a timeout that can be set. And once you have a good idea of how long a process can take that you've written code for, set that timeout accordingly and test against that timeout and stay aware of that as the changes are being made against the code as it's evolving. I think cloud ready it's less about where code runs and more about designing for volatility and external constraints.
Interesting. Thank you. You even knocked one of my follow-up questions on that. But yeah, also, if you could probably help us understand or think about things like stateless design and scalability when building or refactoring systems for cloud. Because now everything containerization is now seen as foundational practice for deploying scalable code applications.
Yeah. So if you think about it at a very high structural level, the key concept that ties almost every cloud resident system, containerization, stateless design, any of those, all of those together, is that they are inherently disposable, right? A container can be killed at any time. A Lambda invocation can be terminated before it reaches a successful completion. Kubernetes pods restarting are probably routine events, right? And actually, even in a server-based context, a virtual machine can be stopped and restarted without warning, right? So recognizing that means designing your processes around the expectation that your hardware can disappear at any point in time. So statelessness in that context is, in a very real way, about making failure of your hardware cheap. If there is no state to manage, there's no need to write code to reacquire that state when a process ends and is restarted. Planning for failures and designing around the idea that recovery from a failure is just starting a new instance is probably if it isn't the most significant shaper of the design decisions, it's going to be near the top of that list. In a container-based context, I think that still holds true. The difference is that the container is, at that point, the smallest unit of replacement, right? The key factor to keep in mind there is making sure that the startup behavior is consistent and predictable. By itself, that alone will ensure that the environments are repeatable, which is what you're really aiming for, and allow a failed container to be replaced automatically and seamlessly rather than relying on any kind of manual troubleshooting process. So yeah, I mean, statelessness and containerization, rather, I think matter more because they make failure cheap and recovery routine than for any other purpose or reason. It comes right down to it.
Yeah, yeah. Any favorite containerization applications you have?
Well, I have not really worked extensively with containerization at a professional level, and I'm just in the process now of kind of building up a home lab. So I've played around a little bit with Docker and Podman. I'm kind of thinking Podman at this point. The trade-offs for Podman are that it's, I think if I'm understanding correctly, it's closer to the hardware, so you get better performance out of it. It's still Docker file compatible-ish, but it's also a lot more, rigid, I guess is a good term for it. A lot more demanding about your Docker files. You can do things with a Docker file in Docker that Podman will not let you get away from. So yeah, favorite, I don't know that I have a favorite at this point, but I'm leaning towards Podman, even though frankly some of the structure and setup is turning out to be somewhat painful.
Yeah, before we talk about, I do have questions about performance over here, but I want to take a question from David, bringing it on stage for you. So
Okay.
David has a question. Do you have an opinion on the Flask framework? Does it scale well?
So I think the scaling was one of those things where it's so context dependent that it's really hard to say. In a containerized structure where your data store is completely separated from your Flask environment and application, and you can spin up and drop, new instances of containers, I think it scales as well as anything else out there. From an individual instance perspective, I honestly don't have enough information to be able to give you a good answer on that. I want to say that it should scale about as effectively as anything else that's out there that serves in that same kind of structure or in that same sort of realm, I guess, for the same sort of purposes. You will probably find that Fast API is going to be more performant, but there's also a lot more work, I think, that has to happen than in a Flask context. And I mean, on the other side of that, if you have Fast API, fastest, most work, Flask is probably about in the middle, good balance between a lot of stuff already supported versus speed of operation. And then at this end, you have something like Django where it does everything for everyone, but it's not going to be as fast. It's not going to be as performant, just at an instance by instance level. After that, it's really going to end up depending on how well you can spread that load out, load balancing across containers running your application, regardless of whether it's Flask or Fast API or Django or something completely homebrewed, is probably going to be where you're going to see the most scalability capability out of all of those options.
Thank you, Brian, for taking up that question. If David, you have any follow-up question, please feel free to post that in the chat. But David did have a good comment. He said, reminds me, based on the discussion we were having, reminds David of an article that he read in Economist about over-engineering software. Like they over-engineered bridges because they knew that faults were going to happen. So engineering team, so you engineer them to be fault tolerant, he says.
Yeah. Fault tolerance is a critical thing, especially in a cloud context.
Yeah. I have a question about Python performance because it has for a long time been criticized, for performance, especially in high throughput systems like microservices. We were talking about containerization. So, in your experience, how does Python hold up in modern architectures built around, containers and microservices compared to other languages like Go? Yeah, because that's being used a lot in Kubernetes and even Docker.
Well, okay, so the simple fact of the matter is that Python is an interpreted language, and interpreted languages are going to be slow, right?
Mm.
So from a performance perspective, there's not a whole lot that you can do about that. I'm hopeful with the changes to the global interpreter lock that are starting to surface in 3.14 that we're going to see more performance capabilities out of that, removal of that global interpreter lock. But I'm not comfortable saying that we're going to or not going to at this point. It's kind of a tough question to answer. So I'm not sure that I've given you a good solid answer for that, in all honesty. Feel free to follow up with whatever else.
Definitely. But also, if you could please touch base on concurrency, because we know Python's performance and concurrency limitations have long been challenged for engineers. So with CPython 3.14, which is set to introduce no GIL, like free-threaded mode that allows true multi-threading. So how do you think Python development will change now? Because it's already there.
Yeah. So right now, I'd wager that most Python code is I/O bound and not CPU bound, and that's where the global interpreter lock is having the most impact. I would hope that the free-threaded model would open doors for other types of applications that are more CPU bound to be written in Python, but really that's just hoping. I wouldn't be surprised if a lot of the I/O bound tendencies in existing Python code was there because of the global interpreter lock. All that said, though, it's worth noting that concurrency is a design problem before it's a runtime problem, right? Having better concurrency support in the language really doesn't eliminate the need to understand how your processes are going to contend against each other, or how to deal with the data ownership and the scope of the code, or how the failures can happen. It's a runtime problem second and a design problem first.
Interesting. Yeah. What advice would you probably give to engineers who would want to write performant Python code or to handle concurrency?
Well, okay, so on the performant code side of things, write your code so that the runtime does as little work as it can, and so that the work that it does do is easy to reason about. And there are several factors that could come into play in that. Making conscious decisions about data structures, for example, to avoid unnecessary copying, or optimizing for runtime performance where it matters for your specific needs. Balance breaking functions out into smaller and more understandable and testable units with avoiding process-to-process boundary transitions. Sometimes those process-to-process transitions get expensive. Not frequently, but they can happen. Above all, lean into making your code clear and changeable, and worry about profiling of the code later, if at all. On the concurrency side, I would say add concurrency sparingly and only when there's an actual benefit to doing so that outweighs any of the overhead that would be needed to handle things like errors or data contention or anything along those lines. Parallelized processing can be really good and very useful, but there are enough additional design considerations that need to be thought through. They might vary wildly from one problem space to another. Worry about it when you understand where the time is actually being spent by your code, and then only when the additional coordination costs and failure handling that you have to build into the code are acceptable from a project standpoint. Optimize for clarity and correctness first. Really only reach for concurrency when you understand where the time is actually being spent.
That's really helpful. Thank you. Thank you, Brian.
Yeah.
I do want to talk about your book. I was just trying to get the link, and I'm going to post that link in the chat so that others can also see it. So you've recently published in December, you published the second edition of Hands-on Software Engineering with Python with us. Yeah, that's the book. Yeah. So tell us what motivated you to update the book now, and what are the major changes, topics in this edition?
All right. Well, good part of it was just the time lag. It was 7 years between the first edition and the second. Python has changed substantially, not just in terms of language features like data classes and type hinting that we've talked about before, but in the maturity of its tooling and the breadth of problems that it's now used to solve. The ecosystem around testing, packaging, automation, and deployment has grown in ways that significantly change how Python is used in real-world systems. Its adoption has also expanded dramatically, particularly in cloud and large-scale environments. And also, we mentioned AI earlier. It's a kind of a go-to language in the AI space right now. While it was already capable in those spaces, the expectations placed on Python developers have grown alongside that adoption. Today, Python engineers are frequently expected to think about architecture, performance, testing, operational concerns, maybe other things in ways that just weren't as common with the first edition was written. All of those growth areas and the dramatically increased surface areas for use of the language, I think, kind of begged for further discussion, particularly since as those grew, the expectations for engineers using it grew right alongside it. The second edition, I think, keeps the same software engineering focus as the first, but revisits it through the lens of today's Python ecosystem, more modern tooling, the kinds of systems that Python developers are now expected to build and operate.
Yeah. And also, we have a new chapter on high performance computing with cloud ready practices throughout.
I don't remember that being in the second edition.
That's not in the second edition? Okay.
I don't believe so.
I thought that was a discussion that we had with my colleagues. Okay. I might have received the incorrect information. Sorry about that.
There might have been in the first edition.
Okay. All right. Also, at this point, anybody from our attendees audience can feel free to ask questions to Brian. Please post them in the question and answer section, please. Because I might also ask you more questions, but since it's a 1-hour interview, I just want to make sure everybody gets a chance to also ask questions.
Yep, sure.
Yeah. Right. While we wait for any questions, I also want to ask, based on your experience in the industry, how do senior engineers influence team velocity, not just through their own output, but through architectural decisions and enabling others?
So the senior engineers and I'm sorry, go ahead. Say again.
It's more from the thought leadership perspective, I'm asking.
Right. So the senior engineer and higher level engineers that I have basically tried to emulate and that I've seen, do the best work, kind of overall, they really aren't defined by the code that they write, but by the systems that they shape and the teams that they're enabling. I mentioned earlier that the focus for a senior engineer, I felt, was more broader system. Why are we writing this code? How does it interact with the other pieces of code? Sometimes that involves some gatekeeping. We don't really want to be going down this particular design path because reasons, whatever the reasons are, or hey, why are we not using this brand new dead sexy library that has just shown up in the last 3 months, whatever, right? There's a lot of broader scope, not quite policy and procedure level things, but asking questions of the less senior engineers and guiding them to learn how to ask those same questions on their own. Why do we go down this road? What is the benefit? How is this better? And what's going to be different if we take this approach versus that approach? what are the trade-offs? Because there are always trade-offs, always, always, always trade-offs. Those are things that I think all of them have to be considered. And the broader that you can spread that as a senior level engineer, the less that you as a senior engineer have to come in and start putting your thumb on the scale. But at the same time, there's got to be some degree of collaboration, because you need to have all of your engineers on the same page. There's got to be buy-in. We're all doing the same, working on the same project, the same code base to get to the same goal. Let's make sure that we're not throwing random roadblocks and boulders in our path to get there.
Yeah. Thank you. We have a question from David. I want to bring it on stage.
Yep.
Interesting.
How much time do you split between coding versus communicating or managing other engineers? I have not had to manage other engineers from a personnel management standpoint for quite some time, which I'm very thankful for. The more people I meet, the more I like my computer, but not as much time writing code as I would like, at least in a professional context. But at the same time, the communication kind of stuff that I just talked about, actually, in a lot of respects, is almost as much fun for me. And it's definitely as challenging in a lot of cases, trying to get, I don't know, a team of half a dozen senior engineers, software engineers, some of whom are senior, some of whom are junior, some of whom are in the middle somewhere, to come to a consensus about how do we get from point A to point B, is frequently a herding of cats kind of thing. There's a lot of communication skills that are involved, and they have proven to be very, very useful in getting to that consensus. And that in turn allows me to spend less time managing that communication and design effort, because people are doing that on their own, and thus spending more time, for me at least, being able to actually sit down and write code. I'm not sure if that answers the question adequately or not. Kind of rambling about my personal experience there, sorry.
Thank you, Brian, for asking that question. And thank you, David. You've asked most of the questions today. Appreciate that. Feel free to ask more questions. I have posted a link for our deep engineering newsletter and publication. So please do subscribe to that while we are still having our discussion. So I think we can take a few more questions. We do have time. I hope that's okay with you, Brian.
Yeah.
Perfect. Yeah. So maybe I could just ask you a few more questions. What's one trade-off you see engineers, especially software developers who use Python, consistently they get wrong when building systems?
The one that I would say is most consistently seen in my experience is kind of going back to the idea, or the comment about over-engineering things earlier. I want to write this as an object-oriented system because object-oriented is the way to go. Okay, it's got its purposes, and I mean the same could be said for, I want to go functional programming. Okay, understand your problem space, right, and design the solution around that problem space, because that's what you're trying to do. You're trying to provide a solution for that specific problem space. I think some variation of that is typically the most common thing that I see people making. I don't want to say wrong decisions, because there may not be wrong decisions, but questionable-ish ones, or decisions that ended up being more costly on a longer term basis than was really necessary. Perhaps the best example in my personal experience was that at one of my previous positions, we had a system that was written in Python, but it was written in Python by somebody who came from a sharp.net background. So the project structure was ridiculously huge. Every function had its own module. Every class had its own module. When you put everything together, the functional layers of the system were 7 or 8 deep, depending on the context there. Way more complicated than it needed to be. And it was hard to manage. It was hard to maintain. If I could have gone back and talked to, let's call him Steve. If I could have gone back and talked to Steve, I probably would have said, Steve, look, there's this really good book out there, Code That Fits in Your Head. Read that. It's all about keeping things at a manageable level, because psychologically, humans can only keep 5 to 7 bits of information in the front of their memory at a given point in time.
Yeah.
You're talking about 7 layers worth of depth here. That's already saturating things in this project structure. And then you also want people to be able to understand how this is linking together. That's 6 more things, even if it's just one connection from 1 to 2, 2 to 3, 3 to 4, and so on down the line. You're oversaturating the memory space right there. Keep it simple. Collapse things down to the point where you don't have to have 19 different classes and 15 different instances of all these other classes to deal with something that really should be capable of being managed as a single function.
That is very edifying. In fact, I saw David.
Keep it simple, Steve.
I saw David posting that right now. Any popular engineering practice you disagree with?
No, not categorically. Again, it's all trade-offs, right? If there is not a compelling functional or policy procedure reason to go down a particular technical path, anything's fair game as far as I'm concerned. It's really, again, constraints and goals, right? When you know what the constraints are, you know where you're trying to get to from A to B, B to C, C to D, all of that kind of stuff. Then you can start kind of winnowing out, this is not necessarily a great idea because it's going to interfere with our B to C chain here. Let's not go down that path. Or, if we have to go down that path because policy reasons, can we come up with some other way to deal with it, that doesn't involve turning this entire B2C linkage in our process architecture into a hairball. That gets very old very quickly and difficult to maintain.
Yeah, thank you. Also, when you look at engineers, how can you tell if someone is ready for senior level work? Tell us that mindset.
It goes back to what we started with, I think. Have they started demonstrating that they're concerned with more than just, is the code doing what it's supposed to do? Is this function working? If I give it A, does it result in Q coming back? Whatever that actually is. If there's a certain amount of curiosity, why are we doing it this way? What is the advantage of taking a functional programming approach versus a procedural versus an object-oriented? I don't know. You tell me. What do you think the advantages are? What are the trade-offs? And do they recognize the trade-offs? Those are the things that I think start really indicating, yeah, somebody is actually ready to go beyond just, hey, I've written this function and it's done and it's tested and it works. Done. I'm finished. Going home for the day.
We have a question that I would like to bring on stage. It's about your book. Wait a second. Yeah.
Should I read the first edition before the second? Well, okay. I'm going to be greedy. Yes, I would like you to read the first edition because that's more royalties for me. But functionally, do you need to? No, you do not. There are things that I think are still worth knowing that are in the first edition that just didn't make it into the second edition, but you're going to find them other places, even just from experience if it comes right down to it. So I don't think that there's a need to do so. As far as the relationship between them goes, well, I started telling a story in the first edition about a fictitious company, Handmade Stuff, and I tried very hard as I was writing that book, that first edition and the second edition, to kind of keep that story moving. So the first edition story is, hey, this is a company that's just starting to get into, we want to develop an application structure to deal with our various issues, problems, what we're trying to accomplish, right, as a company. The second edition kind of picks that up and goes on from that and said, okay, so we have this application and it's functional, but it's less than optimal. And there's a significant impetus on the part of the organization for us to move into the cloud. So what would that look like? And that's the story that I'm kind of trying to tell with the second edition. A lot of the principles are still absolutely the same, right? You still need to have that system level thinking. You still need to understand the problem space. You still have to work out, how are we going to deploy this? What it's going to look like is going to be extremely different because you're not pushing software out to end users, pushing things out to the cloud somewhere, and then making everything accessible through a web interface of some sort. But I mean, the fundamental principles behind those are really not all that different when it comes right down to it. How would I recommend approaching the book to get the most practical value? That's a really hard question for me to answer because I wrote the book, so I don't necessarily have a good readership context. I have looked at some of the reviews of the book on Amazon, and at least one of them flat out recommended, or maybe not recommended, the reviewer flat out said, I just sat down with the examples, not necessarily even with a laptop, I think. I'd have to look this up, and kind of walked through them, at least in my headspace, to figure out how does this apply to what I'm doing today or next week or whenever it is. There really aren't exercises to focus on, and the bulk of the book is one single project for all practical purposes. I have tried to group the chapters into what I feel are kind of logical constructs or logical breakpoints in the various processes, and I'd actually have to go and look at the table of contents directly to give you an example. So system modeling, chapter 4. If you're concerned with data structures, that's probably a good starting point. And then functional development tools. So system modeling, if you're concerned mostly with the logical and physical architecture and how to get communication channels established between pieces of your application. Code style and related standards, if you're concerned with how do we deal with documentation, what should commenting look like, functional code standards, how do you want to manage in an object-oriented context, do you want to have formal properties? Do you want to have just simple duck type things? What kind of type checking and annotation do you want to use? Development tools, pipenv versus poetry versus UV versus whatever else might be out there by this point in time. That particular chapter, I missed writing, or I missed the discovery that UV had the one piece of functionality that I use in pipenv that just wasn't there at the time by something like a week. I would have completely changed the chapter had I discovered that. I mean, just take a look at the table of contents. I think it's reasonably well set up from the standpoint of trying to find what matters most to you. Start there. That would be my suggestion. And to answer David's follow-up question on that, you could read it in order. It works that way. Jump around as much as you feel comfortable with jumping around.
Interesting questions. And by the way, guys, if you would like to read these books, there's PAC subscription that allows you to keep the title, and you can go to PAC website and explore the subscription-based service that PAC offers, and you can read these books as you like. Interesting. Brian, thank you for answering these questions. We've almost come to the end of our conversation, but maybe an advice you would like to give to Python developers trying to grow into becoming stronger engineers as we are in now AI accelerated world,
Right.
where AI is integral part of development now, and all the developmental workflows. So what would your advice be?
I'm going to frame that in kind of what I would like you to take away from the book as a reader. If you come away from the book thinking differently about why you write the code that you're writing, not just how, then I feel like the book has done its job. I mean, end of the day, developers are on the hook to develop and ship working code, right? But yeah, I don't know. I'll go back to my basic principles, I think, more than anything else. Think in systems, design for change. If you're working with a team, optimize for your team as much as possible, because you to be the only person managing a chunk of code or an entire project. It comes right down to it. My hope is that you can apply the principles that you pick up, wherever you find them and whatever they might be, in your day-to-day work. Asking how these code fit into a larger system. How will it change over time? How will our design choices today affect the product later or the people who have to work with it even after you're done with it? That mindset shift, I think, is a key thing in enabling an engineer to grow into more senior roles and to build software that holds up under the real world pressures that you're going to run into.
Interesting. Thanks so much, Brian. This definitely has been a fantastic conversation. Very practical, very grounded, and extremely valuable for engineers looking forward to grow beyond just writing code. Thank you so much for joining us today. And to everyone, if you enjoyed this conversation, please subscribe to Deep Engineering, which is on Substack. We explore topics like software architecture, engineering practices. We talk about system designs and a lot of other things that you would find helpful. So yeah, thanks again for joining us, and we'll see you in the next Deep Engineering session soon. Thank you, everyone. Goodbye.